Welcome everyone to today's talk about the Unreal Animation Framework, our next generation animation system for UE, UEFN, and the open metaverse. My name is Nicolas Frechette, and I am a programmer at Epic Games. Before we start, a quick disclaimer that the technology shown in the Witcher 4 Unreal Engine 5 Tech Demo is under active development and will continue to evolve in the future. To get us started, here is a quick video of some of the animation highlights from yesterday's demo. Nice. To better understand where we are going with the Unreal Animation Framework, it's worth first taking a step back to see where we come from and where we are today. Animation blueprints are 11 years old today. And at the time that we were building it, we had been building games with Unreal Engine 3 for some time, using Unreal Script and simple blend trees. A typical multiplayer match at the time would have had around 10 players, primarily using capsule-driven motion. And the hardware of that era was slowly emerging with more cores, where you could typically find 2 to 6 threads. And so it was in that landscape that animation blueprints were conceived. And we wanted to primarily address 3 things with it. First, we wanted to increase expressivity by moving away from simple blend trees towards more powerful animation graphs. Second, we wanted to unify around blueprints, which were being developed at the time, for a more integrated workflow between gameplay and animation. And third, we wanted to push as much of the animation workload onto the worker threads as we could. And this has proven to be quite successful over the years. And today, in a typical Battle Royale match, you can find 100 players using a mix of capsule-driven motion and root motion from the Nintendo Switch all the way to the high-end consoles. We use animation blueprints extensively for all of this, and the hardware trends have continued in the previous direction. And today we find 8 to 16 threads on common hardware. We've also released the Unreal Editor for Fortnite not too long ago, making game development much more accessible to developers, allowing for a ton of new niche and fun game experiences to be created within the Fortnite ecosystem. And as we look ahead, we have much broader ambitions. We envision an open metaverse where you might have 1,000+ players within a single game experience, powered by multiple servers and perhaps hundreds of threads, using the Unreal Animation Framework. The hardware trends have continued to evolve, with today's CPUs having more cores than ever before. And we're now seeing commonly a mix of slow and fast cores in the hardware. This makes it especially challenging to manage concurrent workloads efficiently, and it is now more important than ever. These are just some of the challenges that we are facing ahead. Let us now focus on some of the unique specifics in the Witcher 4 Tech Demo. A story-driven world like this is rich and full of life, NPCs walk about in the environment, they interact with it, they interact with one another, as well as with the player. This requires careful orchestration with gameplay to ensure contact point fidelity is maintained, and so the execution order is very important. Root motion is also desired for the higher fidelity that we can get, and with it, it brings the need for stitching and warping as we enter and exit contextual interactions, as well as cinematics. And when the story calls for it, NPCs can congregate together in a small area like this. This is the market scene from the demo. In here we have over 300 NPCs. These are not particle system. They are not GPU vertex animated. They are not simple crowd actors. Each and every one of these is a fully fledged NPC with all of the bells and whistles that you might expect. They have slope warping using control rig. They have look at IK using control rig. They are motion matching, etc. All of this is, of course, running at 60 frames per second on a standard PlayStation 5. Root motion in a scene like this is especially challenging from a performance point for two reasons. First, today with animation blueprints, when you rely on root motion, animation evaluation is constrained to the game tread, severely limiting our ability to reach this kind of scale. Second, not only do we have to animate each and every NPC within the view, but even NPCs not on screen or occluded still need to continue updating for us to be able to extract their root motion and move them about the world. And so, to better adapt to this changing world and face these challenges head on, our answer is the Unreal Animation Framework. From the ground up, it has been designed for high performance. We had a mantra going into this that you should pay only for the features that you use, and this has been our guiding principle throughout development. We've greatly minimized game tread interactions, allowing for far greater concurrency than before, and progress continues with our goal to ultimately remove all game tread interactions. We've also greatly improved how we leverage the CPU cache. This supercharges the single-threaded performance, which is as important as ever, whether you run on a small mobile device or on a single-core cloud server. Today, when a graph like this with animation blueprint is too slow to execute, it is common to manually convert it into native C++ through a process that we call nativization. Thanks to our efforts on the performance front, this is now obsolete and no longer necessary, allowing artists to remain fully in control of assets from conception all the way to final release. Root motion no longer has any performance restriction. It is a first-class citizen, and it works regardless of its source, whether it comes from capsule-driven motion, source animation data, or sequencer. It will flow through the graph like any other attribute, allowing you to warp it and blend it however you choose. We also continue to put a lot of effort into ensuring that you can create small and reusable assets to help reduce contention in source control as your projects grow in scale and complexity. We will be introducing skeleton families, loosening the coupling with skeletons, allowing you to reason about them at a higher abstraction level. For example, reasoning about the upper body, lower body, facial curves, and so on, and the runtime will figure out the specifics of what that means for the particular character that the graph is evaluating on. This will allow for easier asset reuse, such as blend profiles, while still allowing for asset-specific overrides when required. We are also introducing trait-based animation nodes. These are fully data-driven. You aggregate traits in a stack similar to how mass traits are used or entity component systems, and it allows you to create bespoke animation nodes where you need them. And this is really the embodiment of the pay for what you use mantra. If you have a sequence player that does not need to synchronize in a group, for example, there is zero memory overhead, zero CPU overhead for that feature on that node. It is never checked at runtime. It isn't there. It is free. We've also continued and greatly improved gameplay integration, giving you more flexibility in how things execute in relation to one another. And similar to animation blueprints, we have thread-safe variables for input into the system, as well as a thread-safe event-based system for inputs and outputs. All of this comes together under a unified pipeline because first and foremost, this is a tactical evolution of our existing framework. Our goal is to be able to reuse as many of the assets that you have today where possible, such as animation sequences, blend spaces, motion matching databases, and so on. We are bringing control rig and state tree closer together with the rest of the animation runtime as first-class citizens. This will come with a consistent user experience, allowing you to move from one to the other in a seamless manner, allowing you to compose them in new, powerful ways. We've also augmented Rewind Debugger with all the new features of the Unreal animation framework, giving you unprecedented insights into everything that goes on within the animation runtime, from how motion matching selects its animation, how animations are synchronizing together within a sync group, to how they blend together and layer to produce a final pose. We've also greatly improved capture and replay performance to be able to work at the sorts of scale that you've seen. Now onto the good stuff. On the right here, you have an image of a capture I took a few weeks ago from a development build. This is in the market where there are over 300 NPCs running at 60 frames per second. And here I have to again point out that even NPCs that are off screen are fully animating, although at the lowest level of detail. In here, we animate over 45,000 bones each frame. And this is split over 800 skeletal meshes. NPCs are built from multiple parts, similar to what you would do today with animation blueprints using copy pose from mesh. The total animation cost is around 52 milliseconds per frame, split over 12 worker threads. As you would expect, NPCs have various levels of details for both visuals and animation. And our cheapest tier runs in about 0.06 milliseconds to 0.12 milliseconds each, while the highest tier with cloth and metahuman facial animation takes about 1.6 milliseconds. We have a budget system to allocate these as you move about the world. And you can see here on the right that the CPU is still idle for a great amount of time. Last but not least, this slide here shows the frame timings for the whole tech demo from start to finish, including the black screens at the start and the end. It's a little hard to see. This is a smoothed graph. At the top, you'll see the smooth blue line there across at 16.6 milliseconds, followed by the yellow line beneath it, which is the GPU time, showing that we are GPU bound, as we tend to be, and as you might expect from the awesome visuals that we've seen. Just beneath it, in the pale blue, you see the game thread time peaking at around 12 to 13 milliseconds there, while smoothed, with the orange and green lines below being the two render threads. And from this, you can see that despite everything we've thrown at the screen, there still remains ample room for gameplay to bring the world alive. And I will now leave it to Samuel to discuss how motion matching interactions were achieved. Thank you.
Thank you, Nicola. Good morning, everyone. My name is Samuele Rigamonti. I'm a principal animation programmer at Epic Games, and mainly focusing on procedural animation and motion matching. So, thanks to the Unreal Animation Framework, we can now afford many actors simulating dense crowds, and within this density, we're now facing the challenge of character interactions. How can we solve them in a simple way that preserves character believability, since character could be walking around, performing whatever the game needs them to do? And how can we maintain budget requirements in check? Well, motion matching already proved to be an effective compromise between performance, as well as being scalable from low-end to high-end platform. So we decided as a starting point, extending it with a few concepts. So we introduced a new post-search interaction asset specifying animation for each possible role actors can take. In the example, we have series mounting animation with the role player, synchronizing with Kelpie animations covering for the role horse. The interaction asset also contains properties about how to calculate and distribute alignment errors. For instance, during gameplay, if actors are not where they should be according to this asset, who do we want to move, Siri or Kelpie? Rule of thumb, a bit of both, but usually the actor that moves the most, that in this case is Siri. Now we group post-search interaction asset in a database, like we would normally do with sequences or blend spaces in a regular motion matching locomotion setup. On the screen, you can see the animation coverage we use for the horse mounting database. And you'll notice that so far, nothing specific to motion matching interaction is here. So let's talk a little bit more about the new concept in the database schema. In regular motion matching, we use the schema channels to tell the system what features we care to match, like feet positions and velocities, and how much we care about them via their weights. For example, translates in sampling the character feet positions relative to the character root bone. But for motion matching interactions, we might want to match Siri's hand reaching for Kelpie's saddle. So we extend most of our channels to support the concept of role. In the screenshot, you can see we're matching the horse position relative to the player's root and vice versa, with their respective roles highlighted. And this is how it looks like from a rewind debugger session, showing some of the evaluated coverage for Kelpie's root bone positions relative to Siri's. You probably see where we're going with this now. Using regular motion matching channels, we can achieve smooth pose and trajectory selections for characters entering interactions, and relying on channels crossing multiple roles to contextually select the best interaction asset that matches the relative positions and orientation of the actors. Let's now look at the setup in Unreal Animation Framework, where through a motion matching trait, every actor publishes its availabilities to participate in one or multiple possible interactions. Availabilities are just pinnable struct specifying what database to use, possible roles, and other conditions for starting the interaction. The trait behaves similarly to the motion matching node we already know, selecting an animation as a result of the search. And since we have spatial information on relative roles, the trait can also calculate the required root motion warp to properly align the actors. Now let's see how the motion matching interaction runtime execution flows. First, all character publishes their availabilities. Then all those availabilities get collected and sorted by the post-search interaction subsystem. Then during its tick groups the actors in multiple islands of possible interactions in different colors on the screen, and generates all the latent motion matching searches that could happen. Excuse me. As final step, the subsystem injects all the required tick dependencies for thread safety and getting ready to perform the searches on the next frame. Now we know the characters, their dependencies, and all the possible searches. We're ready to begin the new frame. With the added flexibilities of UEF, we can use mass in a thread-safe manner to speed up the calculation of trajectories. We then perform the necessary searches locklessly through our motion matching trait and cache them in the subsystem to propagate the result to other actors. We publish availabilities again, and the cycle continues. We'll release in a future version of the game animation sample project an example. But for now, this is what it looks like in action. And here's Adriana from CD Projekt Red to show us how it's being used in their games. Thank you.
Thank you so much. Hi, my name is Adriana Bielak, and I am an animation engineer at CD Projekt Red. Sam introduced a perfect setup because the technology and possibilities that he just laid out speak directly to core challenges that we've been tackling and the ambitions that we have at CD Projekt Red. So what was our core need? When we at CDPR think about building these deeply immersive experiences, our work is often shaped by a few key ideas. You might not find them formalized in a company handbook, but they are definitely a big part of how we approach things. These ideas influence on how we look at new technologies, like the ones Sam discussed, and how we try to push the boundaries of what is possible. So for us, it's felt really important to move beyond the static environments. We are constantly aiming to move to create our world more believable. And the huge part of it is seeing characters in a dense crowd reacting in ways that feel natural and convincing. Think about our marketplaces and our city streets. We really want all those populated spaces to feel authentically alive, bustling with individuals who don't just stand around, but feel and seem to live and feel alive. And this is, for us, the foundation to the kind of immersive experiences we are striving for. While polished, good-looking locomotion is definitely essential and something that we pour a lot of energy into, we've come to realize that it doesn't, on its own, quite get us to that vibrant, breathing world I was just talking about. It's often these intricate little details, the subtle nuanced interactions between characters and the characters and their surroundings that truly make a game world feel alive. And it's this focus on detailed interactions that, we believe, unlocks a deeper sense of realism. Everything we've discussed, this desire for living worlds, the focus on detailed interactions, it all fuels this deep-seated commitment. At CDPR, trying to deliver the highest quality, deeply immersive experiences for our players is what really gets us going every day. So this is the perspective that we bring when we look at new technologies and embrace them. So when we started exploring this new tech that Sam introduced, we decided to begin with some foundational tests. We wanted to really understand its capabilities by focusing on small, but crucial, physical interactions like character bumps. Because, as I mentioned, these details are key to living world. So our very first step was to check how it would work for Siri bumping into static idling with different type of poses, characters, and approaching from different angles in non-scripted way. And now I would like to show you these initial results. So, naturally after that, we wanted to check and transfer this mechanic to more complex scenarios, something what the player would experience in the game. So here we are. We've got the Siri who's walking, we've got the NPC who's also walking, and we also add a slope to check how it should work. My favorite one. All these examples give you an idea how we approached these motion matching interactions. And now I am really excited to present you how all these elements work together, combined one by one in the game. As you saw at the tech demo, applying this technology into our game systems has confirmed that these physical interactions really do work effectively. Knowing that this foundation is solid gives us the confidence to look towards the next steps, like enabling in future interactions between two or more NPCs who are working through the world. And here we've got a really good example for that because we've prepared a dedicated post-search interaction data asset for NPCs greetings. When this motion matching interactions is a huge part to develop for us, now I would like to shift our focus for a moment to motion matched single character animations, because here we also have some really nice improvements with UE5. And before that, sorry, I forget about something really important if it comes to motion matching interactions, because it isn't only a visual showcase, because we've easily integrated seamlessly with our gameplay systems, especially with smart objects, by exposing a flag for our designers to give them really good, direct and granular control, so they could decide at which character and in which smart object it could be bumpable. And now we can shift our focus on the smart objects topic, because these improvements are really nice if it comes to the naturalness. I want to talk you something more about how we set up smart objects, because this topic has been covered by Julius Girbig from CDPR and also Justin He from the Epic Games during yesterday's presentation about locomotion and interactions for hundreds of characters. So if you haven't seen it, I do recommend to watch it. So today I would like to talk you a little bit more about motion matching improvements with UE5, about those effects, and also about modular design here, in terms of smart object entries and smart object exits. Watch this. what you are seeing is powered entirely by motion matching and full root motion. Watch this fluidity and the lack of juttering transitions when the character approaches to the object. And this level of naturalness is something what we wanted. But of course, the true exam is in the gameplay, and we would like to have a universal, general solution not only for human NPCs, but also for animals and for Siri. So we created some more complex scenarios when the character can also interact with smart object entries and exits with other characters. And the perfect example here in the tech demo is the Vegas scenario. And behind that, there's a more flexible technology implementation. This is an animation graph dedicated for smart object entries, which is an abstracted logic and a separated animation module. It contains its own logic. In that case, you can see the chooser evaluation and also some important variables like the alignment transform, which is used also in alignment transform animation notifiers in UE5. Again, more information about this AnimNotify you can find in the Julius and Justin's presentation from yesterday. And here is a true power of UAF, because this animation graph can be injected into any animation module. In our case, we injected our smart object entries animation graph to the NPCs module, but it could be any character. And as you can see, you can do this by a dedicated thread, which also has some important general animation arguments like blending. Before I continue, I have one question. How many programmers do we have right now in this room? Please raise your hand. Wow, cool. Because I've got one hint connected with this topic and with UAF. You can eject your animation graphs through the code. Fully. Thanks to the dedicated new animation data interface in UAF, which I really love, because as a programmer, I love to be able to call everything through the code. So, as you can see, you need to create your payload, and it is essential because it bundles all important, crucial data for you. For example, some custom variables like the chooser table or the post-search interactions data asset. In the second step, you can bind and some of your custom methods. For example, from your custom animation systems. In our case, it was idle animation systems. So as you can see, you can really nice combine your custom stuff with that injection. And finally, you need to pass this payload among other arguments. And again, they are general animation arguments like blending settings. So this programmatically control gives you a really nice opportunity to have a context-aware animation setup. Truly, all these features and approaches unlock a vast range of dynamic gameplay possibilities, fundamentally changing how we can bring our words and our characters to be alive. But for final thoughts, I would like to hand it over to Paddy from the Epic Games. Thank you.
You did great. Hello. I'm Paddy Walker, Technical Product Management Director for Runtime and Gameplay Animation, and I'm going to say basically all the same things that they just said, just sloppier and faster, to summarize the main points that we want you guys to take away from this presentation. So, performance was our real pillar that we had to nail. We had to get that correct over anything else. And we needed something to really push and make sure that we were actually able to do that. And I mean, what better than The Witcher 4 and sort of what they were trying to do and where their goals were. And I think not only have we learned a ton from this, but it's going to guide a lot of our development going forward. So first things first, we're running UAF on all of the characters inside of this demo. It actually wasn't going to necessarily be the case. We were thinking that we were not sure if we would get Siri and Kelpie done, but we ended up getting everything piled on for UAF. And I think it's turned out quite well and really proven out the performance. The other one is that root motion is not traditionally been the best inside of Unreal with animation blueprints. If anyone's seen the dreaded drop-down menu for root motion, it's just not been a strong point of the engine. So we wanted to make sure that it was fully integrated and seamless for UAF. And it was really important for CDPR as well, for the believability and the weight of the characters. And so, of course, we can now warp it through the graph. And again, this was historically not possible and was only evaluated on the game thread. So again, it's been really important for us to make sure that this is really seamless for UAF. So currently, these are some of the tools that or some of the main tools that we have working as experimental inside of UAF. So we've got motion matching, choosers, sequencer, control rig, state tree, which will be our state machine replacement for now. And many, many more, of course. And we're trying to get as many of the systems up and running as quickly as you can, even if it's in an experimental state, so that we have all of the pieces to work with. So I want to sit on this one just for a second, because I think for Unreal, this is a pretty big game changer. No nativization for the animation graphs, especially for any of the technical artists or artists that have worked on games inside of Unreal. It's tough, right? Like when everything gets moved into code, you're sort of locked out of the development side of things, and it goes more towards the engineers, which isn't great. Or you make changes and now the engineers have to do extra work, and it creates these massive bottlenecks that we just don't want. And so yeah, there was no nativization at all. What we built was exactly how we shipped it. And we weren't able to scale this to this many characters and this level of complexity with animation blueprints. And I can say that for a fact because we actually built most of this demo with animation blueprints first before we converted it over to UAF. So we were sort of doing both of them at the same time. So we know for a fact that it was not able to scale, and that this was a big one for us. And then multi-user editing and shareable pieces. So I'm going to sit on the shareable pieces for a second here, because I think one of the goals for us for UAF as we sort of move towards production ready is that we actually want all of the pieces of your game features to be not only shareable across your projects, but shareable on Fab. You can imagine that you create a cool cover system. Maybe it's like a sticky cover system, and you want to publish that onto Fab so that somebody else can grab that piece and drop it into their game. That's what we're trying to build with UAF, and we're trying to make that as seamless as possible as well. So the Unreal Animation Framework, or UAF, is experimental in UE 5.6, but I do want to call out that we are early experimental. We're only focusing on performance, mainly for this, and a lot of the artist workflows and just workflows in general need a lot of love, and that's going to be one of our main focuses moving forward. So please be patient with us, but we are working really, really hard on this. So where are we going? What's next? So I just talked about the artist workflows. That's our number one thing coming up next. We have to prove out how everybody uses the tools and make sure that it's going to be a great experience, not only for technical people, but for non-technical people. We want to bring in as many non-technical artists and animators in as we can. Then we got to build out all the core tools. So I sort of listed out some of them there, but there's some key ones that we don't have currently. Stuff like layering, where you want an upper body, lower body split, and all the tooling around that. We want to really revamp that entire sort of system inside of Unreal, and so we've got some work to do there. And then iterate on the design in Engine. We don't want to just build something and then toss it out and hope for the best. We want to really iterate. We're going to bring in a lot of artists and technical artists to make sure that we're going over and over again and making this as simple and as easy to use for you guys, so that when it's production ready, hopefully it's going to be amazing out of the box. And then finally, I think this one's really, really important. We have to provide concrete in-engine examples of everything that we want to do, including a lot of the stuff that we did in this tech demo. So I do want to sort of make a little quick note here. For 5.6, we did not update the game animation sample project because we were super busy working on all of this, which is a bit of a bummer, and I apologize. But we will be back for 5.7. And we will have examples not only in animation blueprints, but also in UAF of a lot of the stuff that you've seen inside of the tech demo, obviously sans the IP. Yeah, we're going to come back a bit stronger in 5.7 and make sure that we have a lot of examples for you to use, dissect, and then, of course, give us feedback from. And with that, thank you.